Hello, this is the session 4 of our course, Introduction to Differential Geometry. So in today's lecture, we are going to discuss Whitney Embedding Theorem. We are going to discuss a few examples and see sketch of the proof of the statement. Okay, let's start. So when we think about manifolds, the main objects of our course, usually we think about them sitting inside some Euclidean space, right? We think about them being inside some Rn, right? Let's look at a few examples. For instance, when we think about S1, we think about the standard circle sitting inside R2. I guess that's the most common way to think about it. So we think about S1 as a submanifold of R2, right? Or when we think about the two-sphere S2, we think about S2 being inside R3, right? So we might think about S2 as a submanifold of R3. Same goes for the torus. If we think about T2, one way to think about torus is as the surface of donut sitting inside R3, embedded inside R3. So we think about T2 as a submanifold of R3, right? So usually we think about manifolds in the intuitive way, sitting inside Euclidean spaces. S1 is a one-dimensional manifold sitting inside two-dimensional Euclidean space. The surfaces S2 and T2 are two-dimensional manifolds sitting inside three-dimensional Euclidean space, right? So the dimension of the Euclidean space is not unique where we embed our manifold. We can think about the circle sitting inside R3, right? Or R4 or R5 or any higher dimensional thing. But we cannot embed S1 inside R. We cannot think about S1 as a submanifold of R. You can think about it. This is quite straightforward. Same goes for two-sphere. You cannot embed two-sphere inside R2, right? You need at least three dimensions. So what is the least dimension here? What can we say about dimension? So one manifold can be embedded inside two-dimensional spaces. Is it correct to say two manifolds can be embedded inside three-dimensional space? That's the question. And the answer is no. The answer is negative. That's not true. So the counterexample to this statement, to this embedding statement, would be Klein-Bottle, or a counterexample to that would be Klein-Bottle. So Klein-Bottle is this figure you see here. If you haven't seen this thing before, one way to think about it is the following. Think about square, solid square, and suppose we are going to identify these two edges, these two sides. So if we do that, we get a cylinder. Now suppose we are going to identify the other two sides, but in the opposite way. What does that mean? So we are going to connect this black dot to the other one, this dot to the other one, etc. And the final point to the opposite side. So we are going to kind of glue these two sides, but we are going to glue them in the opposite direction. If you do so, you would get this figure here. And here we are kind of imagining this thing inside R3, but note that this is not an embedding. This is self-intersection, right? There is somewhere that this surface is kind of intersecting itself. In fact, Klein-Bottle can be embedded inside four-dimensional space. There would be no self-intersection. There is a way to embed it inside R4 where there is no self-intersection. So this is a counterexample to the statement that any surface can be embedded inside R3. That's not true. More generally, let's say we have an m-dimensional manifold smooth. The statement is that can we always find some n that we can embed m inside our n? And if we can, what is the least value of n as a function of m? So if I tell you what is the dimension of manifold m, can you tell me what is the least value for n that we can be sure that there is an embedding from m into our n? So Whitney answers this question. The Whitney's embedding theorem kind of gives a positive answer to the first question. It says, yes, there is some n, and it kind of gives a value for n. It tells you what is the dimension n that you can find an embedding. Okay, it's in some sense it's sharp. If you want to have a statement for every manifold, kind of Whitney's embedding theorem gives you the answer. So there are two versions. There's weak Whitney embedding theorem. Let's first state that. What is the statement? So suppose M is a smooth M-dimensional manifold. So let's say it's smooth and it's M-dimensional. Then weak Whitney's embedding theorem says there is an embedding from M. It can be embedded into the Euclidean space with dimension R 2M plus 1. So this is weak Whitney's embedding theorem. Okay, so N is 2M plus 1. Also, there's an immersion version. There's an immersion from M into R to M. So you can bring the dimension down, but it might be an immersion. You can bring the dimension of Euclidean space down, but it might be an immersion now. Okay, that's the statement of weak Whitney's embedding theorem. Now, why do we call it weak? Because there's a way to make the statement better. There's a way to make a better bound on the Euclidean space, and it's called strong Whitney embedding theorem. So the strong version of Whitney embedding theorem is quite similar. It says M, an M-dimensional, smooth M-dimensional manifold, M can be embedded inside, where rather than R to M plus 1, it says R to M. So in fact, it is true that you can embed it into R to M. And it can be immersed into R to M minus 1. So here the dimensions are better. But so the first one is an embedding, and the second one is an immersion. It's just that proving strong Whitney embedding theorem is harder. It uses Whitney's trick. It's slightly more challenging than the weak version, right? Okay, so that's the difference. Um, so think about RP2, it's the projective plane, and Klein-Bottle. These are two-dimensional manifolds. We saw Klein-Bottle, and they cannot be embedded inside R3. So here, if we let M to be equal to 2, the least value we get for the Euclidean space where we can embed these into is 4, which is 2M. So in this sense, even thinking also about S1, in this sense, the dimension 2M is sharp, okay, because they cannot embed S1 into R, or we cannot embed, you know, so 2M minus 1 cannot be true. Also for Klein-Bottle and RP2, the least dimension is 4. Therefore, we have it. There's another very interesting theorem by Ralph Cohen. He says there is an immersion of M, an M-dimensional manifold, into R to M minus A of M. What is A of M? Okay, this might be a surprising fact. Think about dimension M and write its binary expansion. So in the binary expansion of the dimension, count the number of ones. Okay? So AM denotes the number of ones in the binary expansion of M. For instance, I mean, M would be something like 1100101, I don't know, something like that. Here, AM would be 4, the number of ones. You can embed your manifold into R2M minus AM, where AM is 4, for instance, here. This is a very strange theorem. This is quite interesting. So it gives a better bound for the immersion. Okay, let's get back to the weak version of Whitney's embedding theorem. I want to just give you the sketch of the proof. I'm going to kind of ignore some details. You can think about it more if you like to fill the gaps. I just want to give you what is the general idea, why it's correct. Just the idea of it, okay? So let's say M is an M-dimensional, smooth M-dimensional manifold. We want to show there is an embedding. let's denote the embedding with iota. There's an embedding iota from M into R to M plus 1. Let's sketch of the proof for this statement. What is the idea of the proof? The sketch of the proof. Okay, there are two steps. There are two important steps. First of all, for simplicity, let's just focus on compact manifolds. The statement is correct no matter if M is compact or non-compact. It's just that proving it is simpler and easier for compact ones. So let's just assume M is compact. Okay, the first step is to construct some embedding of M into some Euclidean space. Construct an embedding from M into some Euclidean space, Rn, where this n can be very, very large. So for some n, right? We want to say there's an embedding into R to m plus 1. Let's first construct an embedding where n is not to m plus 1. It might be billions times m or whatever. Very, very large number n. So the first step is just to construct an embedding into some Euclidean space. The second step is to show, after we know any manifold, or here any compact manifold, can be embedded into some Euclidean space, the first step is to show, as long as n is very large, well, it's larger than 2m plus 1, there is a way to construct a new embedding using the previous one, where we would reduce the dimension of the Euclidean space. So we construct a new embedding into Rn minus 1. Okay, so we are bringing the dimension of the ambient Euclidean space down, and we do that inductively step by step. As long as the dimension of the Euclidean space is larger than 2m plus 1, we kind of step by step modify our embedding to bring the dimension of the Euclidean space down until we get to R to m plus 1. When we get there, we've finished the proof of weak Whitney's embedding theorem. There is an extra step if one likes to prove strong Whitney embedding theorem to reduce the dimension from R to m plus 1 to R to m. So this is the weak version. There would be a next step to embed m into R to m to get the strong version. We are not going to prove this last step here. This last step is kind of more challenging. We are going to stop at R2m plus 1. Okay, great. So we are going to go over the idea of these two steps. Let's start with, of course, the first step. Let's try to construct the embedding. Step 1. Okay, the fact that we are assuming M is compact is quite helpful. We want to find some function embedding from M, right, to some Euclidean space. To Rn, as I said, n can be quite large, right? We want to find this embedding. So f is a map from M to Rn, right? So f can be written as f1 up to fn. It's embedding. Since M is compact, embedding means it's immersion plus it's one-to-one to its image. Okay? F would be from M to its image is homeomorphic. Great. So in particular, F should be injective. It should be immersion and injective. So I should construct a map F from M to Rn smooth map that it's immersion and injective. Let's first focus on the injective part. Okay, great. So F, well, since it's a map to Rn, can be written as F1 up to Fn, right? We can write its components. It would have n components. Each fi, where I is between 1 and n, is a real valued function. It's a map from M to R, right? The fact that the map F is injective means, so number one, the fact that it's injective means for any 2 points x and y in M, where x is not equal to y for any 2 different points, f of x should be It should not be equal to f of y. F of x is not equal to f of y, right? That's the property of the map we are looking for. What does it mean? It means one of the components at least should be different. So there should be some I between 1 and n such that fi of x is not equal to fy. Sorry, fi of y. Fi of x should be different than fi of y. The second thing is that the map should be in immersion, right? What does immersion mean? It means derivative of f at every point x on M should be injective. So df at x must be an injective map. So from linear algebra, we remember a linear map is injective if and only if its kernel is equal to 0. There is no non-trivial vector in the kernel of your linear map. So this means for any vector v you pick in the tangent space of M at x, where v is not the 0, is not the vector 0, derivative of f acting on v is non-zero, which means at least one of the components is not zero. So there should be some I such that dx fi acting on v is non-zero. So we should find functions f1 up to fn with these two properties. Functions f1 up to fn from M to R, such that for any 2 points x and y, one of these two functions fi should distinguish them. And for any x and any vector v, there should be one of these functions where the derivative of fi on v is non-zero. Okay, how can we define these functions? So let's try to define these functions. The essential thing is that we are assuming M is compact, right? That's the assumption we are having here to make things simpler. So let's say this is M. Since M is compact, we can cover M with open sets U1, U2, U3, U4, etc. Each UI is an open set. So there is a covering, and it's finite. So there is a finite open covering of M. Let's denote them with U1, U2, and it's finite. So let's say the last one is UK, right? So there are open subsets of M. So what are the extra assumptions we have? Well, they cover M. So the union of these open sets U1 up to UK, so the union of UI, where I goes from 1 to K, equals M. Also, we can pick these open sets sufficiently small, such that each of them gives you a chart. So for each I, there is a map phi from UI, a diffeomorphism to an open subset inside Rm, right? Just by the definition of the manifold. If these open sets are sufficiently small, which we would assume that, there would be a diffeomorphism from UI to some open set Vi inside Rm. So Phi is a diffeomorphism to Vi, an open subset of Rm. Okay, so these are the set of data we have now. We have a manifold, we covered it with open charts, right? So the essential lemma here, called partition of unity, says, okay, partition of unity. This is an essential lemma. We are going to use this lemma many times. It says there are functions. Let's denote them with row 1 up to row k, associated to these open sets, such that each row I is a function from M to R. It takes the values of row I is between 0 and 1. Okay, so row I is between 0 and 1. For any x, row I of x is between 0 and 1. And it satisfies two properties. Essentially, since our manifold is compact here, there are two essential properties. One is that row I of x equals 0 if x is not inside ui. So if x is inside M minus ui, row I would be 0. So another way of saying this is that the subpart of rho I, all the points where rho I is non-zero there, they're inside ui. So for instance, rho 1 can only be non-zero on this red region inside U1. Rho 2 can only be non-zero on this red region inside U2. Rho 3 can be non-zero inside U3, etc. They must be equal to 0 outside of the corresponding open set. The second property is that any point x you pick inside M, you can look at the value of rho 1 there, rho 2 there, etc. It might be that x is in some different open sets ui, so some different rho i's might be non-zero there. If you look at the sum of the values of all of these functions at x, it should be equal to 1. So this should be the case at any point x in M. At any point x in M, the sum of the values of rho I of x, where I goes from 1 to k, must be equal to 1. Okay, so the lemma says for u1 up to uk, you can always choose these functions. They're called the partition of unity. So let's recap. We can write M as union of open sets u1 up to uk. U1 is diffeomorphic to V1, some open subset in Rm, up to UK through phi k is diffeomorphic to some open subset in rho m. Also, we have these partitions of unity, rho 1 up to rho k. Great. That's the set of data we have fixed on our manifold. Now I want to define the function f, the embedding from my manifold into some Euclidean space. Right. So the function f was supposed to be f1 up to fn. So how am I going to define these functions? So for any point x on manifold, the function f of x is defined to be the following. Look at rho 1 of x, and then rho 1 of x times phi 1 of x. So phi 1 of x is in Rm, and then multiply that by the real value number or real valued function rho 1. And then the next thing would be rho 2 of x, rho 2 phi 2 of x, up to rho k of x times phi k of x. So list all these functions. Note that rho 1 takes values in R, phi 1 takes values in Rm. Same goes for each rho I. Rho k takes value in R, rho k phi k takes values in Rm. So f of x, what is the range of f of x? So f of x, you see, the dimension of the image is Rm plus 1. We get that k times. So f takes values in m plus 1 times k. So we have a map f from our manifold M into Rn, where n is k times m minus 1, where k is the number of open sets we are using to cover our manifold. So we might use many open sets. So k might be very large, so n can be very large. So the claim is that the function f defined this way into rk times m plus 1 is an embedding. That's the essential claim. If you prove this, we have an embedding from our manifold into some Euclidean space. Okay, so let's rewrite the claim. We say f, the way we defined it, is an embedding from m into rk m plus 1. So I should show f is injective. Since m is compact, it's enough to show it's an immersion, injective immersion, because the properness follows automatically. Let's start by showing f is injective. Okay, so suppose we have f of x equals f of y. Proving f is injective means we should show x is equal to y. So we should show x must be equal to y. Right. That means f is injective, right? Okay. The fact that f of x is equal to f of y means rho I of x, so all components should be equal, right? So rho I of x should be equal to rho I of y for all I. And rho I of x, phi I of x should be equal to rho I of y, phi I of y, again, for all I between 1 and n. Also, since we have sum of rho I of x is non-zero, it's equal to 1, there must be one index in this family, let's say j, there must be some j, such that rho j of x is non-zero, right? So there is some j between 1 and k, such that rho j of x is non-zero. It can't be that all of them are 0 and their sum would be equal to 1. Great. But rho j of x is equal to rho j of y, and they're non-zero. Furthermore, rho j of x, phi j of x, should be equal to rho j of y, phi j of y. Another fact, if rho j is non-zero, it means x and y should be equal to uj, right? Because rho j is only non-zero inside uj. Rho j is 0 outside of uj. So x and y, both of them are in the open chart uj. That follows from the fact that rho j is non-zero. Since rho j of x, phi j of x, is equal to rho j of y, phi j of y, and rho j of x is equal to rho j of y, and they're non-zero, we can cancel them from both sides of the equation. So phi j of x is equal to phi j of y, but phi j is a diffeomorphism to its image, right? It's diffeomorphism to some open subset, so it's injective. So x must be equal to y. So we proved x is equal to y. It shows f is injective. Now, I leave the immersion part as an exercise to show the derivative of f is injective. This is not very challenging. It's a good exercise. I leave that to you if you like. You can think about this more. Okay, let's recap. So we constructed an embedding from M into some Euclidean space. So the manifold M now can be embedded into Rn. Also, the manifold is smooth. We assumed it's compact. As I said, the compactness is not essential. So we have embedding into Rn, where n is k times n plus 1, a large number. The second step is to bring this dimension down to m plus 1, to 2m plus 1. So reduce the dimension n as long as n is larger than 2m plus 1. Okay, how are we going to do that? Let me first tell you what is the essential idea of doing this, and then we would kind of prove that more rigorously. So as I said, we want to use f to produce a new embedding into Rn minus 1. Okay, so how can we do that? Okay, great. So the idea is essentially using a projection. So the essential idea is, let's say this is our abstract manifold M. We have an embedding f into some Euclidean space Rn. Let's say schematically this is Rn. And let's say the image of f is something here. Let's say this is image of f. So this is the manifold M embedded inside Rn. Now, if you pick a generic vector v, if you just choose some vector v in Rn, we can look at the subspace orthonormal to v, orthogonal to v, right? Let's denote that with v perp, the hyperspace that is normal to v. So this would be this red thing. This red space, hyperspace, this is an n minus 1 dimensional thing. So this is essentially Rn minus 1 sitting inside Rn. Like in this example, it's like R2 sitting inside R3. Now consider the projection from Rn into this hyperspace. Let's denote that with pi. Let's kind of project everything from Rn to this space which is normal to V. So this is a projection map, right? So we project everything down. So the projection of the image of f in particular would be something like this. So by combining these two maps, if first F act on M, we go to Rn, and then we apply the projection, we go to Rn minus 1. So the claim is that if M is an embedding, for almost any choice of V, as long as n is larger than 2m plus 1, this composition is still an embedding. So this way, we bring the dimension n down by 1. We combine the embedding we had with projection, we get a new embedding. So that's what we want to prove. The goal is to prove, um, we want to show there is some vector v inside Rn such that when we look at the projection given by projecting to the normal direction of v, if we combine that, compose that with f, this is still an embedding from m to Rn minus 1. That's the goal. In fact, as long as n is larger than 2m plus 1, of course we can pick some v. It's much more is correct. The point is that almost any vector v you choose, this composition would be an embedding. So it's much more than that. It's not that there is one v. It's that almost any vector, if you choose a random vector v, with probability 1, this is going to be an embedding. This pi projection to the hyperspace normal to v composed with f would be an embedding. Let's have an observation. I want to prove this, right? I want to say what is the idea of the proof. Let me kind of define something. Let's have an observation. So the point is that if we pick vector v, or if we pick the vector 2 times v, or minus 3 times v, the direction they give us, they're the same, right? If this is v, this is 2 times v, this is minus 3 times v. The plane, which is normal to these vectors, they're always the same. So the projection map associated to v or 2v or minus 3v, they're all the same. So in some sense, choosing v or 2v or minus 3v, it doesn't make any difference. So it's like we're picking a vector in Rn, but mod some equivalence relation, where v is the same as a non-negative real number times v. Rn mod out by this equivalence relation is denoted by Rpn minus 1. This is an n minus 1 dimensional manifold. So it's essentially the equivalence relation is v is the same as a real number c times v, where c is a non-zero real number. This is an n minus dimensional manifold. It's essentially because we have Rn, we kill one dimension by saying, v and 2v and 3v all are the same. So we show the class that v belongs to with this bracket v inside Rpn minus 1. So rather than saying we choose v in Rn, it's better to say we pick a class of v in Rpn minus 1. Associated to that, we get a projection map. We compose that projection map denoted by, say, pi v perp, or the class of v perp, with f. We get a map from M to Rn minus 1. We want to say for almost any choice of V or class of V in Rpn minus 1, this composition is an embedding. Right, that's the more accurate of statement of what we want to do. So for almost every choice of class V inside Rpn minus 1, the map defined by pi v perp of composed with f is an embedding. Again, proving this is embedding would reduce to 2 steps. First, I should show this is injective, again, because the domain is compact and it's immersion. If M was non-compact, I should have shown it's also proper. Okay. Again, we're assuming n is larger than 2m plus 1. This is the constant assumption we have in the background. Okay. So let's start with showing that this map for almost any choice of V would be an injective. How are we going to show that? So you might have seen arguments like this before. So let's kind of review the proof. Um, Again, I would show first it's injective. I probably would lead the immersion part to you as an exercise. Let's see why it must be an injective map. So suppose it's not. Suppose that there are 2 points, x and y in M. So we're doing proof by contradiction. So let's say there are 2 points, x and y in M. I mean, it's not exactly proof by contradiction, but we will see. Let's say we have 2 points, x and y in M. They're not equal, but the value of this map, pi of on x and y are equal. We want to say for almost any choice of V, this would not happen. So this is M. We have 2 points, X and Y, distinct points. They're not the same. And then we have embedding F. We embed these into Rn. So we have image of F here. So there is f of x and f of y. Note that f of x and f of y, they are not equal because f is an embedding. We know f is an embedding. So we have image of f inside Rn, f of x is not the same as f of y. But then when we compose this map with a projection to the direction normal to v, we are assuming that then pi of of x equals pi of of y. So it must be that after taking the projection, f of x and f of y, they collapse to the same point. So schematically, let's say this is the image of projection, and f of x and f of y, they go to that intersection point. They go to the same point in Rn minus 1. If that happens, if you look at the vector which connects f of y to f of x, it must be that that vector should be parallel to v. If that wasn't the case, if f of x was somewhere else, where f of y to f of x, if you were connect them, was not parallel to v, f of x and f of y would have projected to two different points on Rn. So the fact that f of x and f of y project to the same point in Rn minus 1, it means the vector which connects f of y to f of x is parallel to the vector v. Okay, so this means if they're parallel in Rn, it means one is a constant multiple of the other one. So f of x minus f of y equals a non-zero real number c times v. So c is a real number and it's non-zero, right? So what does it mean in the Rpn minus 1? Remember, if two vectors are a constant, non-zero constant multiple of each other, their classes are the same. So the class of fx minus fy is the same as the class of the vector v. So they're the same things in the Rpn minus 1. Okay, this is the crucial understanding here. If pi associated to v or f is not injective, the class of f of x minus f of y is equal to the class of v in Rpn minus 1. I want to say for almost every v, this would not happen. Okay, so the trick is defining a new function. So this might be a bit tricky if you see this for the first time, but it would become very clear very soon why we are doing this. We define a new function L defined on the product of M by itself minus the diagonal. I would define what is the diagonal. Let's denote the diagonal with delta to Rpn minus 1. So what is the diagonal? Diagonal is a subset of M times M where we have points of the form x and x inside M times M where x is in M. Note that remember from the product of the manifolds, any point in M times M has the form X and Y. Okay, so if this is M and this is M, schematically, their product would be this square. The diagonal delta is like the diagonal part of this product space. Okay, so points in M times M are of the form X and Y. The diagonal are of the form where x is equal to y, so it's essentially x and x. So what is the definition of this map L defined on the complement of diagonal? We take x and y, we send it to a class of fx minus fy. So if x minus fy is something in Rn, the class associated to this would be in Rpn minus 1. So this is the definition of L. So the essential thing is that pi associated to VOF of x is equal to pi OF of y, projection to the complement of the normal space of V composed with f, for some x not equal to y, if and only if, well, we learned fx minus fy has the same class as V in Rpn minus 1. But the left side, the class of fx minus fy, is exactly Lx and y. So this happens if and only if the class of V is equal to L of x and y, which means if the class of V is in the image of L, right? So the class of V must be in the image of L. So if we pick a vector V such that pi of f is not injective, that implies the class of V must be in the image of L. But the point is that for almost any choice of V, the class of V would not be in the image. For almost every choice of the class of V in Rpn minus 1, the class of V would not be in the image. Why is that? So if I prove this, this implies for almost any choice of V, if it's not in the image, then for almost any choice of V, we do not have this equality. Why is that? Look at the map L. What is the dimension of the domain? Domain is m times m. So the dimension of the domain is 2m. What is the dimension of the range, codomain? Is n minus 1. So since n is larger than 2m plus 1, n minus 1 is larger than 2m. So the dimension of target space is larger than dimension of domain. When that happens, if you map some lower dimensional object into some higher dimensional object, the image inside the higher dimensional space would have measure 0. For instance, think about mapping R2 inside R3. Its image would be a surface inside R3. Almost any point you pick inside R3 would not be on the image of your map. So here, the map L is a map from 2m dimensional space into n minus 1 dimensional space, from lower dimensional space to higher dimensional space. So almost any point you pick inside target would not be on the image of L. In other words, image of L has measure 0. Therefore, any vector v you pick, it would not be on the image. Therefore, pi v perp f would be injective. This is actually called the trivial case of Sartre's theorem. Sartre's theorem says that's the case. So that means for almost any choice of v, v would not be in the image, which means for almost any choice of v, there would not be 2 points x and y where pi v perp o f of x equals pi v perp o f of y. So for almost any vector v, this map would be injective. And note that now this map maps m to Rn minus 1. So in an inductive way, we can continue doing this. We can go from m to Rn minus 1, and then n minus 2, and then n minus 3, etc., until we get to 2m plus 1. Then Sartre's theorem doesn't work anymore. So that's the limit. Also, I leave the immersion part to you as an exercise. Again, immersion part is an application of the trivial case of Sartre's theorem. Proving this for the strong version that you can embed this into R2M is kind of more challenging. It would be good if you like to think about that. It's related to something called Whitney's trick, which also appears in in problems related to Poincare conjecture in higher dimensions, and Smale's work on H-cobordism theorem, etc. So this is a very interesting subject. You can try to see why you can't just apply Sar's theorem. Also, we proved this for compact manifolds. As I mentioned, this is also correct for non-compact ones. So it's a great exercise to see how you can extend the proof to non-compact manifolds. I leave that also as an exercise. Okay, in the next session, we will start Riemannian geometry. So we will start studying in the next lecture Riemannian manifolds, Riemannian metrics, connections, geodesic, etc. Okay, great. It's a good place to stop.